Welcome to In Depth with Academia. I'm Richard Price, CEO of academia.edu. And as always, I want to thank you for tuning in with me today. So, what we do here each time is engage with a fascinating piece of research, just kicking the tires, looking at the arguments, and really trying to see what's in it for you, the listener. Today, we're exploring a thought-provoking paper by David Lush. Again, I want to remind you, I'm not here to endorse the research, but to lay it out neutrally so you can decide what resonates. All right. So, David Lush's paper, Does Bohm's Quantum Force Have a Classical Origin?, asks a bold, seriously intriguing question. Can the mysterious quantum force that appears in Bohmian quantum mechanics actually have its roots in classical physics, specifically classical electrodynamics? That's a lot to unpack, so let's break it down. First, the core of the challenge. In the de Broglie-Bohm interpretation of quantum mechanics, sometimes called Bohmian mechanics, there's a quantum force that explains some truly counterintuitive behavior of electrons. For example, in the ground state of the hydrogen atom, this quantum force completely cancels out the regular electrical attraction, the Coulomb force, between the electron and proton. It's almost like, magic? Or is it? But you might wonder, what's even the big deal here? Why care if this quantum force has a classical origin? Well, if it turns out that the weird quantum stuff scientists observe can actually be produced by old-school classical forces, that could mean our understanding of the quantum world needs a pretty big update. It could help unite classical physics and quantum mechanics, or at least point us in a direction where quantum weirdness might just be a sophisticated result of familiar forces. So, what exactly does Lush propose? And, how does he get there? The main idea hinges on something called Zitterbewegung, which, it's a mouthful, is this jittery, ultra-fast motion theorists think electrons might be doing, almost like they're orbiting in tiny high-speed loops at the speed of light. If you imagine for a second an electron as a point charge zipping around like crazy, that's Zitterbewegung. Now, Lush notes that if you take two such electrons, both executing this circular speed of light dance, the magnetic force that arises between them in certain circumstances can actually match the Coulomb force in both size and the way it falls off with distance. That's surprising. Digression alert here. There was this one time I misread Zitterbewegung as zebra wing, and for a day I thought physicists were naming things after animals. Anyway, back to Lush. If those two dancing particles are aligned in their spin but out of phase, the magnetic force between them is equal but opposite to the usual electric attraction. In other words, the electron wouldn't fall into the nucleus because the magnetic force would perfectly cancel the electric pull. And this is key. That's exactly what Bohmian mechanics says happens, but without explaining the mechanism in classical terms. Lush is suggesting maybe this isn't just quantum magic, but an effect classical forces can create. He goes further. When the two particles move relative to each other, the shift in the pattern of their magnetic force follows a spatial rhythm matching the famous de Broglie wavelength. That's the same wavelength that explains electron diffraction and a lot of other quantum oddities. So, classical forces would not only mimic quantum behavior in static situations, but also reproduce textbook quantum patterns as particles move. All right, let's talk methods for a sec. Lush mainly works through classical electrodynamics. No fancy new equations, just the old equations Maxwell gave us, applied in a new context. Instead of postulating a quantum force, he's looking at what happens when you do the math for magnetic interactions between these ultra-fast Zitterbewegung particles. Lots of detailed calculations, but the big idea is simple. Alignments, phases, and motion all matter a lot more at the scale of the electron than we might have thought. Crucially, he doesn't claim this explains all quantum behavior, but raises the possibility that at least some of the famous quantum forces could emerge from the known rules of magnetism and electricity. It's bold, and while it doesn't settle the debate, it's a step, or maybe a nudge, toward thinking differently about how the quantum and classical worlds relate. So, what does this mean for you, sitting in your car, walking your dog, or wherever you're listening? Well, it's a reminder that science is always probing, questioning, and turning things upside down. Quantum mechanics, for all its weirdness, is not a closed book. Theories are proposals, not revelations from above. Sometimes the answers are buried in details we think we've already mastered, And sometimes a single idea like Zitterbewegung leads us to new fascinating possibilities. As always, keep in mind, I'm presenting David Lush's research neutrally. You should engage, ask questions, and decide what fits with your view of the world. Academic work is about insight, not dogma. If you found this intriguing, or if you want to dive deeper, you can check out the paper on academia.edu. That's it for this episode of In Depth with Academia. I'm Richard Price. Stay curious, keep questioning, and remember, the search for understanding never stops. See you next time.